So with instrumentation, you can get detailed measurements, and we have a way to throttle away instrumentation in those lightweight functions that execute frequently. And you can get an accurate profile based on instrumentation hooks that are inserted in the code. Okay. Okay, so in short, if you want to measure your application, you just launch it with a tool called TAU exec. If there is one thing that you take away from this presentation, it's that to measure your application, take your uninstrumented binary, install TAU, launch it with TAU exec, generate detailed data at the level of different runtime systems and IO and memory data, and then you can enable other options in TAU. There is a quick start where you can launch TAU exec with the EBS or event-based sampling option. That means you periodically interrupt the program, measure the time spent in the whole program on the CPU side, but you can also measure with OpenMP, pthread, Python codes, even CUDA using the same tool. And then you can launch the paraprof tool and visualize the performance data. This is the manager window. You can see all the other windows here. There's a thread statistics table. You can see the statistics and the time spent in the application. There's a top level timer called the .tau application. That just means that it's from the start to the stop of that particular thread. And you can see the thread statistics table, even delve deep down at the statement level. Here it's saying that at line number 339, it took so many seconds in the code. And with this paraprof browser, you can just keep all the threads of execution in their own space and functions. So you can see the MPI activity, CUDA activity, OpenMP, and even kernels that execute on GPUs. Here is a thread statistics table again with Python, and you can see the details at the source level. I just want to show you some examples. So here is an example of using TAU to see the data transfer between the host and the GPU and the volume of data that's going between the host and the GPU, bytes copied. You can look at the Python with MPI. You can use it with AI/ML frameworks. And you can even unwind full call stacks when you take a sample. So you can see exactly where the application was spending time. Here is an example of TensorFlow, where you can see the time spent in various locations, including kernels running on the GPU with TensorFlow and which threads executed what kernel. Again, TAU supports Python, TAU supports CUDA, so AI/ML frameworks can uninstrumented be launched with TAU, and you can see details of what kernels were executing on which GPUs and which CPU threads. We have support for call site profiling that pinpoints where a particular function was called, IO profiling, which shows you read, write bandwidth, bytes written to each file, like this. So file by file, you can see exactly which files your application touched. And it has a 3D profile browser, paraprof, where you can have crosshairs that show you the intersection between the function and the thread, and communication matrix displays, and trace analysis tools like JumpShot, which ships with TAU, or the Chrome browser, or Perfetto, which you can use to visualize flame graphs. Here are examples of tracing with GPUs, and you can see the execution in perfetto.dev. It's a tool developed by Google for trace visualization. And TAU can generate events, traces that can be fed into Perfetto. This is a view of Ampere, the trace visualizer from TU Dresden, with Cocos runtime system. And we have support for many other runtime systems. Now we of course support MPI, where we support the PMPI as well as the MPI tools interface. You'll hear about the MVAPITch tool that provides access to TAU for key events through the MPI tools interface, where we can see the performance variables going right deep into the MPI runtime, as well as having support for control variables where you can modify what the MPI runtime is doing. We have support for pthreads, OpenMP, OpenACC, OpenCL, CUDA, level 0 for Intel, ROCm, Cocos, and Python instrumentation. And you can mix and match these runtimes as well. All you have to do is launch your code with the TAU exec tool like this. So you can enable ROCm or level 0 or CUPT or OpenACC or even OpenMP tools interface, OMPT, like this. And you can set the variables at runtime to change what gets measured through the runtime environment variables. So in case you would like to install it, you can install TAU on your laptop like this, and then you can use it. Now, coming to the second part, when our tools and other packages need to be installed in a consistent way, we have the extreme scale scientific software stack, which coming from the software technology team of the Exascale computing project, targets many of the applications and tools developed in ECP. Now in ECP, as you know, we have previously had support for GPUs from just one vendor, but as we are going into the next generation, we have support for not just the Summit and Sierra type of systems which come from IBM, but also systems from HPE and systems that use GPUs from 3 different vendors. And our goal is to build a software stack that allows developers to be productive. And there are many different technical areas such as programming models and runtime, development tools, software ecosystem that ECP software technology project uses. And we aim to have quarterly releases of E4S. We just did a release for supercomputing, and this is a 22.11 release. But E4S is a community effort that aims to provide open source software packages for developing, deploying, and running scientific applications on HPC machines. And we have a software stack that's curated based on the stack package manager. And we have over 100 different HPC and AI/ML tools that include TensorFlow and PyTorch. And we have binary build caches, we have container images, we have base images as well as full featured images. So you can create custom solutions, and you can have support for GPUs from all 3 vendors. We also have a partner organization, ParaTools Inc., that provides support for ECP, for maintaining an issue tracker, for installing on the HPC systems, and for application development engagement. And supports commercial cloud platforms with multiple MPI implementations. E4S includes not just Intel MPI, but also MVAPITch 2 and NVHPC and MPITch and OpenMPI on the cloud platform, so that you can replace one distribution with another using a tool called E4S Container Launch or E4S CL, where a containerized application can have its internal MPI substituted with the system MPI. And you can find out more information about E4S at the web page. Let me just show you that now we have over 100 different HPC projects that are now shipping in E4S. And we use the stack package manager. Because scientific software is becoming incredibly complex and hard to install. Okay, here is a dependency tree of NALU, a NALU CFD application. And you can see that NALU depends on Trilinos, it depends on Boost, and all of these tools. Here is another graph for Deal2 FEM package. And there is RMiner, And you get the idea. Our tools are becoming very complex. There's a lot of dependency. Even proprietary codes are based on open source libraries that need to be built in. This is also the case for the Zeiss circuit simulator that we heard about in FA SOC talk earlier, that there is a complex dependency tree and you need to have a consistent software stack that has components like Trilinos, like BLAS, LAPACK, all of these built in a binary form that you can easily use to assemble your full stack. And we are building an entire ecosystem of multiple applications, packages, platforms, compilers, programming models, and that leads to a combinatorial explosion. And it's gotten so bad that people are now having a situation where they are employing multiple FTEs just to build and support an application. And we must make it easier to rely on other people's software. But how do you install software on a supercomputer? You first of all download all the tarballs. If your Zeiss application uses 16 packages, you will just download all of them and start building. And when you start building, you fight. You fight with the compiler. You fight with the flags. You fight with the makefiles. And you tweak all this until you finally get a binary that at least builds. And when you run that binary, you don't know what will happen with this complexity. And you finally, after doing all this, you get an application binary, you run that, and it seg faults. And then you start all over again. And there has to be a better way. Now you may say, what about modules? Well, modules don't install the software. It's just an interface to set paths that somebody else has installed. And we support modules as well in SPAC. So to use SPAC, just clone it, source the environment, and just install it. I also recommend that you do the compiler find and external find to set up other packages. You can say SPAC install TAU or TAU version 232 with GCC compiler, with 9.3.0, with CUDA, with MPI, with Python. But you can specify that, no, I don't want any other MPI. I want MVAPIX2. MVAPIX2 version 2.3 without the RAR path argument. So you can customize your installation of TAU very easily. And then you can SPAC find and it will show you all the packages that it installed. This is a view from the recently released 22.11 SPAC. But you can visit spac.io for more information. We are using SPAC in the E4S to build containers. And if you're asking, what are containers? Well, a container is a lightweight collection of executable software that encapsulates everything that's needed to run a specific task. You can think of it as everything except the kernel of the operating system. And various approaches. There's the type 1 hypervisor, type 2 hypervisor, and container. The containers do not have the kernel, it's the base operating system, just the libraries. If you want to learn more about containers, we have a tutorial tomorrow, a full day tutorial at SC using containers to accelerate HPC. And here is the E4S download page. You can download the containers from Singularity. We have support for full featured images for x86, IBM PPC64LE, which supports NVIDIA as well as ARM. And you can just do a Docker pull if you would like, or you can use the full featured images or base images. We have some containers like this on Docker Hub that have been very popular. This is over 1 million downloads to that. And in this piece, you can see all the 100 different packages that you can use. So if you are building a software stack for your ASIC simulation codes, you can use packages pre-built. Here is support for 3 different GPUs on x86, and also PyTorch, TensorFlow, ParaView, Visit, Julia, and Python. And we have support for IBM. This is a container that we have just released today. You can see the 22.11 release for IBM, PPC64LE, and it has support for AI ML packages like TensorFlow, PyTorch, with support for GPUs as well as Julia, Python, NVHPC 22.9, the September release for Power. And you can see all the packages and which ones were using GPUs. And here is TAU, Trilinos, and other tools. And go to Docker Hub and download this container for IBM 9. And how we build Trilinos with different variants. We have a build cache with over 92,000 binaries, which have various combination of architecture, compiler, and operating system for each of those binaries, as well as images on AWS. If you're coming to the tutorials, you'll likely be using one of these AWS images, which has a host of different packages, gives you a remote desktop environment with TCV. And also we have VirtualBox images and a tool to replace the MPI between the container and the system. So in short, I think of E4S as a conduit for future leading edge HPC software, targeting the scalable next generation computing platforms. And it has emerged as a top level component in the DOE HPC community. And much of this work goes on in Eugene at the Performance Research Lab at the University of Oregon. We have a very active developer visitor program. If you would like to come visit us, consider coming to Eugene. And I would like to thank our sponsors, including the Department of Energy, the European Union, Admire Euro HPC JU project, the Department of Defense, NSF, NASA, CEA, industry partners including IBM, Intel, NVIDIA, AMD, ARM, and our partners at various institutions, including the Ohio State University, the Paratool Sync, University of Tennessee, Knoxville, TU Dresden, and English Supercomputing Center. And we would like to thank the Exascale Computing Project for their sponsorship of TAU and E4S. And with that, I'll take any questions.